Okay, we should be live. Yeah, hopefully I'm using the correct microphone and everything. Well, at least we have some sound coming through. That's great. Okay, let's do the robot business. Unless we have a human to talk to. But no, we currently don't have anyone available, so I'll have to go for the robot. Have to go for the robot. What website are we developing?
You're developing a website that focuses on biomedical data applications, incorporating gamification to engage the general public. Your site, bionichaos.com, hosts multiple Flask web applications that are single-page client-side processed and avoid using React, AWS, Google Cloud,
Yeah,
and
that's fine.
Socket.
Let's focus on what we have, not what we are not doing. Actually, in the more recent applications, I'm trying to avoid the Flask, so everything is JavaScript. What do you think?
Using JavaScript for your recent applications aligns well with your single-page client-side processing approach. It allows for a more streamlined and responsive user experience, fitting
Can you
perfectly with
do
your goal.
shorter responses and avoid any fluff? So we are live streaming at the moment. We have the website open. I can't share the image with you, like not with the current model, but we would like to give an overview of the website, the future directions, and also the Flask versus vanilla JavaScript. Can you touch on that? Can you just do super quick responses?
Certainly. Your website, bionichaos.com, hosts interactive biomedical tools with a focus on gamification. You've been moving away from Flask in favor of JavaScript for more dynamic, single-page applications. This shift enhances speed and interactivity, key aspects of your user experience.
Well, yeah, that sounds good, but does it actually work? We do still have some Flask applications on the website, but the more recent stuff is pure JavaScript.
Exactly. Your recent applications are primarily built using pure JavaScript, moving away from Flask. This shift allows for more dynamic and responsive web applications, enhancing the user experience on your site.
This one have some shortcuts for.
Yes, using pure JavaScript can streamline development with shortcuts like ES6 features, async await for asynchronous operations.
No, I have no idea what you're talking about. Let's go back to the website. So currently looking at Seizure Zone. I think we did cover it in the previous video.
Yes, Seizure Zone is one of the tools on your website. It's focused on analyzing EEG data for epileptic seizure detection. We discussed its features and how it aids early detection and intervention.
I might have to open another chat because this one I cannot share. Do you know anything? Do you know anything about the new model with Canvas, or I don't think there's point about asking you about yourself, is there?
I can't provide details about my inner workings or the new model with Canvas. I'm here to help with any questions
Okay,
or topics you want to discuss.
okay. Just yeah.
Got it.
There's a few issues. I did cover them last live stream with the different types of models you're using, including the so this is the new voice. Just put it away on another screen because there's nothing to see there. I don't know why it's even.
Got it. You covered different models during your last live stream. If you need to discuss anything specific about those or other website features, just let me know.
Yeah, let's mute it for a sec. I'm not sure. I think you have only like 1 hour to use it. The new voice model. Not sure about that. Maybe they changed it. They keep changing things like on a daily basis. Everything is a prototype. Yeah, we have a few applications still in the works. So we have this pressed MNIST, whatever that's the dataset name that we actually have to include in the description and everything. And hopefully I will be training models. There's some on the website, they have results of they have results. Yeah, dataset collection. What's classes? There's 2 classes. Why is it saying normal, benign, malignant? There's only benign, malignant. Yeah, the interesting thing, if we now chat with this voice model, let's actually close the previous one because we kind of got stuck with it. We actually can chat about what we currently have open. Can browse the web as well. Yeah, and we have some code, so we'll be training. There are some performance of existing models that we would like to compare with. Last time, so we did train something, but the performance was nowhere near other models that were trained. Okay, let's actually use a real-time speech visualizer. Yeah, we'll actually pop it. So can you search for the dataset and the results? I think there is a website for this dataset as well. If you can look it up, I forgot what the link is. I forgot what the link is. Yeah, just go one by one. Okay, there's a website called MNIST. Right, that's correct. And we are looking at the Brest. The Brest MNIST. The good thing about it is some training. So there were models already trained. Yeah, and we have area under the curve of 0.9, which is pretty high. So that looks pretty promising. We would like to replicate that. Can we turn into, no, so we can't turn into the canvas. Right, so we have this project structure. We did export the images, so now we only have two labels. It's benign and malignant. There's no free labels. I don't know where you got the information from before. That's incorrect. We're storing the model checkpoints, but they're quite large. We probably don't, I don't know if we need them. Maybe not, or yeah, we'll just keep them for now. And then eventually we'll try to turn the model into a web version, so we can simply deploy on the website. So essentially you could upload a new image and it will use that model to tell you if benign or malignant. Obviously we need the appropriate disclaimers and everything. Let's just do a project tree quickly. We need to do it from the correct folder, just so the robot knows what we have. So we have that index.html. We'll open it in the terminal. We have this command tree project structure. Okay, we have this project structure. Oh, okay, the exported images just for the example on the site. The actual images are in this compressed file. Then we have the model stored both in H5 and Keras. Apparently, so Keras is the new one, H5 is the old one, but when we actually try to convert the model into a web model, we actually need the old H5 for whatever reason. But yeah, not sure what's going on with that. Yeah, so if you can explain quickly, I'll share the project structure, and then the training code I think will be next. So yeah, I obviously need some guidance. Let's see what's going on. Can you just give the summary and next steps in continuous text? Because I'm actually using text to speech, so no dot points or code in your response.
To move forward with your BreastMNIST project, start by converting the pre-trained model stored in the .h5 format into a format compatible with TensorFlow.js. This conversion is crucial because it allows the model to run directly in the browser. Once the conversion is complete, ensure that the converted model files are placed in the appropriate folder, likely the web model directory, which will store everything needed for deployment. Next, update your index.html file to integrate TensorFlow.js and handle the model loading process. The page should allow users to upload an image for classification, so add functionality to pre-process these images by resizing them to match the input size expected by the model and normalizing the pixel values. With the pre-processing complete, you can feed the image into the model and display the classification results, such as whether the image is benign or malignant. Finally, make sure the tool includes the appropriate disclaimers, emphasizing that it is for educational purposes and not for medical use. Thoroughly test the tool with exported images to confirm its accuracy matches expectations, ideally close to the reported area under the curve of 0.9. Once this is achieved, you can proceed with deploying the tool to your website for public access. Let me know if you need assistance with any of these steps or further clarification.
Yeah, so I have a bunch of tools on the site. Go check them out. I keep saying the same thing. Actually, the robot is probably more humane. It's probably me repeating the same things over and over again. The robot can actually do much better. actually sound more human than myself. Yeah, we have some relatively new tools. We have this joint time frequency scattering for enhanced seizure detection. This is obviously, well, not obviously, I'm not sure if it's obvious or not, but it is synthetic data. Every time you actually increase the data length or change the data length, you get a new EEG baseline with some spikes on it, and the scattering transform is actually highlighting these spikes, and you can see how the spectrogram for it changes as well. Yeah, and there's a description at the bottom of the page. It's not just filtering, by the way. And let's get back to this quickly. Yeah, we had some issues with the training. We might want to train again. I think we already did it twice. If we could actually store the iterations of the training, that would be great. So I want to do it similar to the rhythm scan that is training on different dataset, different images. It's actually EEG turned into spectrograms, but then I like how the results are being presented. So we would like to do the same for the breast MNIST dataset, for the malignant, non-malignant images of the breast. But if you can look at this image, this is another example that we have on the website. I would just like to do the training and everything in a similar fashion in terms of the output of the training. We want to display the accuracy and loss plot, the confusion matrix, and the misclassified images. Maybe not all of them in this case. In the rhythm scan we only had 600 images, but now I'm pretty sure we have some way more. So the misclassified images would be just examples, just selected few. But yeah, we would like the training log with all the parameters as per the image attached. Yeah, I like the continuous text because we can actually read it out loud before I'm totally losing my voice.
To replicate the structure and presentation style of the results shown in the image for your breast MNIST project, you can implement the following steps. When training the breast MNIST model, store all training iterations, including accuracy, loss, and validation metrics, so they can be displayed for each run. This will allow you to track the model's progress across different epochs and compare results over multiple runs. Once the training is complete, generate plots for accuracy and loss across epochs, similar to the image. Use libraries like Matplotlib or Seaborn to create these visuals. For the confusion matrix, calculate the model's predictions on the test dataset and display the matrix as an image, ensuring clear differentiation between benign and malignant classifications. To address the misclassified images, select a small representative subset instead of displaying all misclassifications, particularly since breast MNIST likely has many more images than your EEG example. Finally, the training log should include details such as test accuracy, training and validation accuracy and loss, model settings, and key parameters like batch size, learning rate, and optimizer. Storing these logs in a structured format, such as JSON, will allow you to dynamically generate the results page, enabling a seamless display of the plots, matrix, misclassifications, and logs. By integrating these features into the BreastNIST visualizer, you can replicate and enhance the level of detail and interactivity seen in RhythmScan. Let me know if you need specific code for implementing these features.
Get a quite convoluted. Yeah, this will get quite complex. So we also have obviously we have all the code for RhythmScan, and we'll actually want to see if we can essentially do the same. So I might share the code with you, or should I share the structure for the project? Yeah, it has a lot of PNG images. Well, RhythmScan has actual images, but the breast MNIST has it doesn't have the raw images. It has a folder, a file, compressed file with all the data in it. So that will be the main difference. But yeah, but if you can have the code for RhythmScan as reference, that will be great. But I'll just share the project, the RhythmScan project structure with you.
Looking at the structure of the RhythmScan project, the main difference between it and the Breast MNIST project lies in how the data is stored and accessed. RhythmScan uses uncompressed folders with categorized image datasets, while Breast MNIST relies on a compressed.npz file to store the data. To adapt the RhythmScan code as a reference for Breast MNIST, you would need to add a pre-processing step to handle the compressed dataset format, extracting and organizing it into a structure similar to RhythmScan before training or visualization. The static folder in RhythmScan contains results folders for each training run, storing logs and outputs like training plots. To replicate this functionality, the Breast MNIST project should implement a similar mechanism, automatically generating and saving results after each training iteration. This will allow dynamic visualization of metrics such as accuracy and loss, confusion matrices, and sample misclassifications. The training scripts, such as trainbetter.py, can serve as templates. Modify them to accommodate BreastMNIST-specific parameters such as its image size and binary classification tasks. The front end in the template's index.html file will also need adjustment to reflect BreastMNIST-specific terminology, such as benign and malignant instead of seizure and non-seizure. The app.py file provides the backbone for the RhythmScan project. Use it as a reference to set up a similar Flask application for BreastMNIST, ensuring that the workflow for training, saving results, and displaying visualizations remains consistent.
Okay, so couple of things. So first of all, we want to move away from Flask. So yes, we're doing all the training in the backend, which should be okay, but happy for you to comment on that. Then we each iteration of the training, we would like to store the results and display performance like we do with RhythmScan, like in the image I shared with you earlier. So we would like to replicate that. The loading of the file, loading of the data can be custom for the BreastMNIST data file. I think it's a compressed data file, but yeah, I don't care how you process it. So the most efficient way, you can choose which way you prefer. Yeah, if you quickly can comment. And what was another point? Yeah, so to sum up, we don't need Flask in this case, I don't think. Well, let me know if we do. But essentially, I don't run anything in the backend. I think eventually, once we deploy the web model, can the web model, considering it's Keras JS, so it's like a minimized version of Keras, that should be able to run in JavaScript. Is that correct? Can you quickly comment in continuous text?
Moving away from Flask for this project is a good choice if you want the entire workflow to run on the client side without relying on a back-end server. This approach simplifies deployment and ensures the application is self-contained, especially since TensorFlow.js supports running machine learning models directly in the browser. By converting your Keras model to TensorFlow.js, the training and inference processes can be implemented entirely in JavaScript, eliminating the need for Flask or back-end computation. For each iteration of training, you can store results such as accuracy, loss, and validation metrics directly in browser memory using JavaScript objects or local storage. These results can then be dynamically displayed on the page, replicating the performance visualizations seen in RhythmScan. For the accuracy and loss plots, you can use libraries like Chart.js or D3.js to generate and update them in real time as the training progresses. The confusion matrix and misclassified image display can be implemented similarly by updating the visualizations dynamically based on the training output. Loading data from the compressed bremnist.npz file can be handled by pre-processing it beforehand into a more convenient format, such as a directory of images. Alternatively, you can load and parse the .npz file directly in JavaScript using TensorFlow.js's tf.data API, which supports custom data loading pipelines. The choice depends on whether you want to keep the pre-processing step external or integrate it fully into the web application. Using TensorFlow.js to deploy the model is indeed a feasible solution. Once the model is converted to TensorFlow.js format, it becomes a lightweight, browser-compatible version of the original Keras model. This version runs efficiently in JavaScript and can leverage hardware acceleration via WebGL. By taking this approach, you ensure that the tool remains scalable, responsive, and accessible to users without requiring back-end infrastructure. Let me know if you'd like further details on implementing these aspects.
Yeah, I'll just quickly share with you some code, and I'll just want you to quickly comment. It's really for your reference. We might need to redo the code from scratch. So first is the rhythm scan that is already deployed and running. It's running well, so we're not making any changes there. That's the one using Flask, but don't worry about it. Sorry, so that's the one we use for training. So that's just for your reference. You might want to make suggestions as to how we should train differently for the breast MNIST dataset. But it's just but this is just a reference for what worked for us before. Just after a quick comment on that code, and just keep it as reference. Hey, can you just give me a quick text summary?
The provided rhythm scan code demonstrates a robust back-end training pipeline using Flask, handling data loading, training with Keras, and generating performance visualizations like accuracy loss plots, confusion matrices, and misclassified image displays. It's designed for
So we are moving away from Flask, eventually just training on the server, but then just using JavaScript for displaying the results of the model, so the performance of the model. on a HTML page, and also later on deploying to the web-friendly version of the model as well. So users can upload their own images and get results. How does that sound? Just a quick response using continuous text would be great.
For a dataset stored in folders, with the training process and results logged dynamically into structured files for each iteration. For BreastMNIST, the primary difference lies in its compressed .npz file format, requiring a pre-processing step to load and split the data. Since you're moving away from Flask, the training workflow would ideally shift to client-side processing or pre-training offline, with the model converted to TensorFlow.js for browser-based deployment. Visualizations and results logging can replicate RhythmScan's outputs, but should be implemented directly in JavaScript to match the new deployment approach. The ConvNet architecture and training settings can be adjusted slightly for the grayscale BreastMNIST images, ensuring compatibility with its dimensions and binary classification task.
So I assume we're using dimensions of the images as they are. I'm not sure. I assume they're consistent. We have to probably check the metadata for the images for dimension, or I'm not sure if we have to check each image individually. How do we figure that out?
Displaying the model's performance on an HTML page sounds like a great way to make the results interactive and user-friendly. You can include performance metrics like accuracy, loss plots, confusion matrices, and selected misclassified examples directly on the page. Deploying a web-friendly version of the model using TensorFlow.js will allow users to upload their own images and get real-time predictions in the browser, making it both accessible and efficient without relying on a backend. This approach aligns well with your goals and minimizes complexity while maintaining functionality. Let me know if you'd like detailed steps for implementation.
Yeah, so we'll have to change what we are currently doing. So the export images Python code is just exporting 10 examples that just place on the front page just for reference. Then we have reviewing the data code. I'll share some of the code with you below, so you know how what works. Yeah, I'll share the review data and the output of it as well, just for your reference. And we will, and let me know what next steps are. We're still not writing code, so no code in your response, just continuous text would be great.
The code and output show that the dataset is well structured with clear training, validation, and test splits. Each image is already resized to 224 by 224 pixels, and the labels are consistent across splits. The images have not yet been normalized, as their pixel values range from 0 to 255. Additionally, the label distribution in the training set is imbalanced, with significantly more samples for label 1 than label 0. This imbalance might affect model performance and will likely require techniques such as weighted loss functions or data augmentation to address it. The next steps should include normalizing the pixel values to a range of 0 to 1 to improve the model's convergence during training.
Okay, we're already doing normalization in the code. I haven't shared the training code with you yet. We did test it a couple times. We had some issues with that code. But again, can you just text only without generating any code? Just give me a quick overview of this code, and also generally what is it we're trying to do as well. That would be good. Yeah, in the original performance, we just did accuracy. We didn't do area under the curve. We would definitely like to include the areas under the curve. In addition to
This code
accuracy,
sets up a comprehensive training pipeline for BreastMNIST, handling everything from data pre-processing to training, evaluation, and model conversion for deployment. The dataset is loaded from a .npz file, and the images are normalized to a range of 0 to 1 before being reshaped to include a channel dimension for compatibility with convolutional layers. Class imbalance is addressed using computed class weights, ensuring fair learning across the two categories, benign and malignant. The model is defined as a sequential convolutional neural network with 3 convolutional blocks, followed by fully connected layers with dropout for regularization. The binary cross-entropy loss function and metrics like accuracy and AUC are used to evaluate performance. Data augmentation is implemented with rotations, shifts, zooms, and flips to improve generalization. And training parameters like epochs and batch size are input dynamically, adding flexibility. Callbacks for early stopping and checkpointing ensure the best model is saved during training. After training, the model is evaluated on the test set, and performance metrics, including accuracy and AUC, are reported. The model is saved in both .keras and .h5 formats, and there's an option to convert it to TensorFlow.js for browser deployment. GradCam is included to generate interpretability heat maps, helping visualize which regions of an image influence the model's decision. The script also outputs a classification report and confusion matrix for further evaluation. The next steps involve refining the workflow to ensure all key results, such as accuracy, AUC, confusion matrices, and GradCam heat maps, are displayed on an interactive HTML page. The TensorFlow.js conversion prepares the model for deployment, enabling users to upload their own images for predictions. Addressing any training issues, such as hyperparameter optimization or augmentation tweaks, can further improve performance. Let me know if you need clarification or guidance on any specific part of this pipeline.
Yeah, we're really going into the woods on this data set. Yeah, before we had the Python thing, sorry, a Flask. So this thing has a Flask backend, so the data is stored on my server, and I'm serving it that way. That's with rhythm scan. We are now trying to improve it. We're actually using a different data set. So this one has this breast scan images. I think they're CT scheme images. Yeah, if you can confirm, pretty sure they are CT. But yeah, they have, some of them are benign, some malignant. We have 3 different folders. So the page, the HTML currently is just showing examples of the 10 images that we exported from the dataset. We might have to export them all, but probably won't display them because it will make the web page too slow, potentially. If you can comment on that. I'll share the HTML code with you as well for your reference. Yeah, we don't want it to be as heavy as this one. This tool is quite heavy as well. The vision impairment simulator is a bit heavy as well. We would like to avoid things like that. I think this is also because it has a Flask backend. We would like to avoid that because I can actually hear my CPU, GPU going when I'm using this. So I'm not sure. It should work on your end as well, but yeah, I think it must be the GPU. Anyway, dealing with different images now. And yeah, we'll have a similar display. Do we need a train test validation? The image I'm attaching, if you can comment on that one, is to do with so someone already did training on this dataset and had some great results with it. So we will essentially trying to replicate those results. So if you can comment on the results quickly, that will be awesome. Yeah, just continuous text. We are not developing any code. I'll also share the HTML for the page. Yeah, we might split the application into 2, so have a similar interface as the rhythm scan to begin with, just to show the performance of the model, and then potentially we'll have another page where you could load your own images. How does that sound? Or would you recommend combining the 2? So I'll share with you both HTML scripts. First, what we currently have for the breast MNIST, and I'll also share what we have for the rhythm scan, which is already deployed. So we would like for the breast MNIST page to eventually look similar to what we have for the older rhythm scan. Let me know, how does that sound? And while it's generating, go check out the website. There is this vision impairment simulator. If you haven't tried it out yet, go do so right now. And there's many other tools as well.
The attached table shows benchmark results for different machine learning methods on the BreastNIST dataset, evaluating both AUC and accuracy metrics. ResNet 18 at 28 by 28 resolution achieves an impressive AUC of 0.901 and an accuracy of 86.3%, which is slightly lower than Google AutoML Vision's AUC of 0.919, but comparable in terms of accuracy. The ResNet 50 models, while performing slightly worse overall, still offer competitive results. AutoML methods like AutoSclern and AutoKeras show solid performance, making them viable alternatives for automating model optimization. Given these benchmarks, your goal to replicate or improve upon such results is ambitious yet achievable. Using a pre-trained ResNet 18 or ResNet 50 as a baseline for transfer learning could help you reach similar performance metrics, particularly if you adapt the model to the 224 by 224 resolution used in your data. This requires training on your specific dataset with class balancing techniques and careful hyperparameter tuning to prevent overfitting, especially given the label imbalance. For deployment, separating the performance display from the image prediction interface is advisable, as it keeps the application lightweight and modular. Initially, you could implement a performance dashboard like the one in RhythmScan to showcase metrics, visualizations, and sample predictions. Later, add a separate page for user-uploaded image predictions, leveraging TensorFlow.js for client-side inference. This division will ensure a smooth user experience while maintaining high functionality. Let me know if you'd like specific guidance on prioritizing these tasks.
Can you also explain how is it even possible that the ResNet 18 performed worse with more pixel data, with higher pixel resolution images? Can you comment on that quickly?
It may seem counterintuitive that ResNet 18 performed worse on higher resolution images, 224 by 224, compared to lower resolution ones, 28 by 28, but there are a few plausible explanations for this. 1. Overfitting to noise in high-resolution data. Higher resolution images include more pixel data, but not all of it is necessarily useful for classification. This additional data can introduce noise or irrelevant details, causing the model to overfit on these less significant features and perform worse on unseen data. 2. Model capacity versus data complexity. ResNet 18 has a relatively small capacity compared to deeper architectures. While it can effectively handle low-resolution images by extracting key features, higher resolution images may overwhelm its limited capacity. This mismatch means it may not learn the additional details effectively. 3. Pre-processing issues. If the dataset at 224 by 224 was not pre-processed properly, such as inadequate normalization, resizing artifacts, or inconsistent augmentation, it could negatively impact model performance. For instance, resizing from 28 by 28 to 224 by 224 may stretch or distort important features, reducing their clarity. 4. Task-specific patterns. For this dataset, the key features distinguishing benign from malignant may already be well captured at low resolution. Increasing the resolution might not add meaningful information, but instead amplify irrelevant details, making the task unnecessarily complex for the model. To address this, you might explore techniques like fine-tuning a larger model, e.g. ResNet 50, for 224 by 224 data, optimizing pre-processing pipelines, or using dimensionality reduction techniques to focus the model on relevant features.
We are live streaming at the moment. Can you do shorter responses? Wait, we might actually try. How about we try chatting with this thing? Hey, can you quickly summarize the last response, like in 2 sentences? Get rid of all the fluff.
ResNet 18 likely performed worse on higher resolution images because the additional pixel data introduced noise or irrelevant details, leading to overfitting, while the model's capacity wasn't sufficient to handle the complexity of larger images. Additionally, the low resolution data might already capture key features, making the higher resolution unnecessary for this task.
Okay, can you give a quick summary for the whole conversation, just in case someone joined us live right now? Just a quick summary without the fluff for the whole thing.
We discussed adapting a BreastMNIST training pipeline without Flask, focusing on client-side deployment using TensorFlow.js for image classification. Key points included normalizing data, handling class imbalance, benchmarking against ResNet models, and displaying model performance metrics on a lightweight web interface, with plans to separate performance visualization from user-uploaded image predictions.
Okay, can you ask me questions about what I uploaded so far and about how we prefer moving forward?
Do you plan to replicate the high-performance ResNet 18 results from the benchmarks or experiment with other architectures like ResNet 50? How should we handle the dataset's label imbalance? And would you prefer focusing on class weighting or augmenting underrepresented classes? For the HTML interface, do you want to separate performance metrics and user-uploaded image predictions or combine them into one page? Lastly, should the application prioritize lightweight deployment with pre-trained models or support client-side training as well?
No, I think so. To the last question, I think client-side training will be too much. What do you think?
I agree. Client-side training would be too resource-intensive for most users, especially with a dataset like BreastMNIST and models like ResNet. Pre-training the model and deploying it in TensorFlow.js for client-side inference is a much better approach. This keeps the application lightweight while still allowing users to upload images and get predictions efficiently.
Okay, what were the other questions, the previous questions?
The other questions were, do you want to replicate the ResNet 18 benchmark results, or would you prefer experimenting with architectures like ResNet 50? How do you want to handle the dataset's label imbalance by using class weighting or augmenting the underrepresented class? And for the HTML interface, would you prefer separating performance metrics and user-uploaded predictions into 2 pages or combining them into one?
Can we go with one question at a time? So what do we currently have in the code? What are we using for training at the moment? Can you briefly, quickly explain?
Currently, the code uses a custom CNN model with 3 convolutional layers for training, along with data augmentation and class weighting to handle label imbalance. It also includes callbacks for early stopping and checkpointing, and it saves the trained model in both .keras and .h5 formats, with an option to convert it to TensorFlow.js for deployment.
Okay, that sounds really good. How is it better or worse than ResNet 18 or ResNet 50?
Your custom CNN is simpler and lighter than ResNet 18 or ResNet 50, making it faster to train and less resource intensive. However, ResNet architectures are more powerful due to their depth and residual connections, which help them learn complex patterns and avoid vanishing gradients. For breaststemnist, ResNet models might perform better at capturing subtle features critical for classification, especially on higher resolution data.
Can you go into the details some more? What's the difference? So what do we currently have? Like how many layers, so on and so forth, and compare it to ResNet 18? I thought ResNet 18 will be actually a fairly simple model.
Your current custom CNN has 3 convolutional layers, followed by max pooling and fully connected layers, making it relatively shallow. Each convolutional layer extracts basic features, while max pooling reduces dimensionality, and the dense layers perform the final classification. This simplicity makes it fast to train, but limits its ability to capture complex hierarchical features. ResNet 18, while simple for a ResNet, is much deeper, with 18 layers of learnable parameters. Its key advantage is the use of residual connections, which allow the network to skip layers and preserve gradients during backpropagation. This architecture enables the model to learn deeper feature representations without suffering from vanishing gradients, making it more effective for complex patterns like those in high-resolution medical images. In comparison, your CNN, 3 convolutional layers, shallow depth, no skip connections, simpler and faster to train but limited in feature extraction. ResNet 18, 18 layers, deeper architecture, residual connections, more computationally intensive, but better at capturing subtle and complex features. While ResNet 18 is relatively simple compared to ResNet 50 or deeper models, it is significantly more powerful than your current model due to its depth and use of residual learning.
So I generally don't want to go for a complex model without any specific need. I would like to actually train quickly with what we currently have, and yeah, we'll just go from there.
That makes sense. Starting with your current CNN allows for faster experimentation and iteration. If the performance is sufficient, there's no need to move to a more complex model right away. Let me know if you'd like help optimizing or analyzing the results from your existing setup.
Can you quickly list, we might want to update the training Python script first. Can you list all the items that we discussed that we need to check if the current code is doing or not? As particularly thinking saving the training result performance and displaying it in a similar way like we do for rhythm scan.
Here's a quick list of what to check and update in the training script. 1. Ensure training results, accuracy, loss, AUC for each epoch are saved to a file or database for later display. 2. Save plots of accuracy and loss curves after training, similar to rhythm scan. 3. Implement saving the confusion matrix as an image for visualization. 4. Capture and save a subset of misclassified images with their true and predicted labels for display. 5. Verify if class weights are applied correctly to handle the label imbalance. 6. Ensure model checkpoints are saved during training for reproducibility and fallback options. 7. Confirm proper formatting for exporting the final model in .keras, .h5, and TensorFlow.js formats. This will align the BreastNIST tool's training output with the RhythmScan interface.
Are we also doing that visualization, the GradCam visualization? Can you explain that quickly? And yeah, we'll go from there.
Yes, the current code includes GradCam visualization, which provides interpretability by highlighting the regions in the input image that most influenced the model's prediction. It computes a heat map over the last convolutional layer by backpropagating the gradients of the predicted class, showing the areas with the most significant contribution to the decision. The heat map is then overlaid on the original image to visually explain the model's focus. This is particularly useful for breast-MNIST, as it can indicate which regions of a breast image led to a benign or malignant classification.
So this is what I currently have for the code. We might need to go over it and restructure. Can you overview the code and provide instructions as to how we need to change it? But don't generate any new code in your response, or any code in your response, just continuous text.
The current code effectively sets up a pipeline for training and evaluating a breast-MNIST classifier, with functionality for data augmentation, handling class imbalance, saving checkpoints, and generating GradCam visualizations. However, there are areas to review and modify to align with the goal of integrating results into a display like rhythm scans. Here's an overview and instructions for necessary updates. 1. Data loading and pre-processing. The current code loads data from an .npz file, normalizes it, and reshapes it to include a channel dimension. Ensure the reshaping is consistent for all inputs and verify that normalization is applied correctly to prevent errors during training or inference. 2. Class imbalance handling. The code calculates class weights using compute class weight, which is good for balancing the loss function. Confirm these weights are passed correctly during training and review whether additional augmentation of the minority class might help further. 3. Training parameters and callbacks. Training parameters are dynamically input by the user. You might streamline this by setting defaults or optimizing batch size and learning rate based on experiments. Early stopping and checkpoint saving are well implemented, but should ensure the best model is saved for evaluation. 4. Grad visualization. The code generates a GradCam heat map for a single test image. Expand this functionality to allow generating GradCam visualizations for misclassified images or specific samples of interest. Save these visualizations in a structured format for later display on the web interface. 5. Performance metrics and visualization. The script prints evaluation metrics and saves models, but does not save accuracy loss curves or confusion matrices in a reusable format. Update the script to generate and save plots for these metrics in designated directories, ensuring they are easy to access for web display. 6. Misclassified images. While the confusion matrix is generated, misclassified images are not explicitly identified or saved. Modify the script to save a subset of these images, including their true and predicted labels, for detailed analysis. 7. Model conversion for deployment. TensorFlow.js conversion is included as an optional step, which is appropriate for browser-based deployment. Verify the converted model works correctly and ensure the directory structure for storing these files is clearly organized. 8. Output structure. Organize all outputs, metrics, visualizations, GradCam images, misclassified examples, and logs into a structured directory hierarchy, making it straightforward to integrate them into the HTML interface. These changes will align the script's output with the goals of displaying detailed performance metrics and visualizations while preparing the model for efficient deployment. Let me know if you need further clarification on any step. I've updated the code to ensure reshaping is consistent for all inputs and added a verification step for normalization, making sure it's correctly applied. Let me know if you need further adjustments or explanations. I've updated the code to confirm that class weights are properly used during training and added additional augmentation to address the imbalance in the minority class. Let me know if you need further adjustments or explanations.
Yes, what we did really quickly is, yeah, by the way, go check out this vision impairment simulator. But what we are doing, we have this new data set that we're looking at. It's called breast MNIST. It has benign and malignant CT scan images. Can you actually confirm that this is CT? Or is it some other type of image?
I've streamlined the training parameter input by setting default values for epochs, batch size, and learning rate. Additionally, I've ensured that only the best model is saved during training by modifying the checkpoint callback settings. Let me know if there's anything else you'd like to adjust.
Anyway, obviously the robot can explain it much better than I can, than I could ever explain anything. I think it's game over for teachers.
I've expanded the GradCam functionality to generate heat maps for all misclassified images. These heat maps, along with their associated metadata, are saved in a structured format for later use on the web interface. Let me know if you need further modifications or additional features.
Okay, we'll need to update, obviously, the front end as well. But we'll do it later on. Just need to do another round of training. We did 2 training runs already. We didn't get we got like 0.7 or so as opposed to 0.9 for area under the curve. So we're trying to improve the model performance. We have apparently a much simpler model than ResNet 18. Well, definitely simpler than ResNet 50. But that's okay, because we don't wanna increase the model complexity unnecessarily. Yeah, so we're making some changes. We have another developer, another tab of ChatGPT, which is essentially another developer updating the code for us. And I'll share the updated version with you below.
I've updated the script to generate and save accuracy loss curves, confusion matrices, and classification reports in designated directories. This makes it easier to access these metrics for web display or further analysis. Let me know if you need any more adjustments.
Yeah, this impairment simulator, I can actually hear my CPU, GPU going. It's a bit too heavy, especially when I'm making changes on the page. I think it must be the GPU then. Yeah, I don't know if there's interest. We might look into redoing it from scratch. That one from memory is a Flask application, but we gearing towards doing vanilla JavaScript because it's then can be streamlined and much quicker for the end user as well. You want to close it. I save a lot of electricity by not using it, but yeah, let me know what you think.
I've modified the script to save a subset of misclassified images along with their true and predicted labels for further analysis. These images are saved in a dedicated directory, making them easy to access for review. Let me know if you need any additional changes or explanations. I've updated the code to ensure the TensorFlow.js converted model is saved in a clearly organized directory, TensorFlow.js Scores model. This helps keep the directory structure tidy and makes it easier to locate the converted files. Let me know if you need further changes or if you'd like to verify other parts of the script.
Yes, I'm not sure if it's a problem specifically for if it's a problem for this specific for or with canvas thing. It keeps giving me errors that the code is too long. That's a bit unfortunate. So we did everything up to 6. We did everything up to change a recommended necessary update number 6. So we would like to stage it and do the rest separately. But can you check the script? So far, yeah, give a quick overview. Don't generate any code yet, just tell me what's going on. So we have another developer essentially implementing changes that you suggested. He went over 1 to 6. So we still haven't done 7 and 8, but can we check the code up to this stage? What do you reckon? It's going places now.
The updated code implements significant improvements based on earlier suggestions, addressing points 1 through 6 and partially covering point 7. Here's an overview of the changes and what remains to be done. Overview of the current code. 1. Directory setup. Separate directories for checkpoints, training plots, misclassified images, and GradCam outputs are now created, ensuring better organization of results. 2. Dataset handling. The dataset is normalized, reshaped, and augmented appropriately. Class imbalance is handled using a mix of class weights and additional augmented samples for the minority class. 3. Training parameters. Defaults for training parameters like epochs, batch size, and learning rate are provided, and user inputs are streamlined. This makes the process flexible while maintaining clarity. 4. Model definition and training. The custom CNN model is well defined, and callbacks such as early stopping and checkpoint saving ensure efficient training and model preservation. 5. Performance visualization. Accuracy and loss plots are generated and saved, providing a clear visual representation of model performance over epochs. 6. Evaluation and outputs. The test set evaluation generates accuracy, AUC, a confusion matrix, and a classification report. These outputs are saved as images and JSON files for further analysis. 7. GradCam visualization. GradCam heat maps for misclassified images are generated, saved, and accompanied by metadata in JSON files, which is excellent for interpretability. Remaining changes. 1. Model conversion for deployment, point 7. While the TensorFlow.js conversion code is included, it depends on user confirmation. Ensure this process works seamlessly and validate that the converted model performs as expected in a web environment. 2. Streamlined results for front-end integration. Point 8. Results such as GradCam heat maps, misclassified images, accuracy loss plots, and confusion matrices should be packaged or referenced in a structure compatible with the front-end interface. Simplify access for visualization on the HTML page. Suggestions. Moving forward. The updated code is well aligned with the training and analysis goals. Focus now on ensuring that results integrate smoothly into the web interface. Validate the TensorFlow.js model on example inputs to ensure it matches the Python-trained model's performance. If performance issues persist with the GPU usage on the front end, consider simplifying front-end visualizations or caching results to reduce runtime load.
Okay, we'll try it again. I'm not sure why is it saying the code is too long. Well, I mean, yeah, it's currently just over 300 lines. That should be okay, shouldn't it? Yes, let's actually try doing a change number 7, see how it goes. It seems like the chat doesn't know what's happening in the canvas. I actually got an error message when generating the code. I got an error message that it's too long and the code in the canvas got truncated. Can you just comment on that? Might need to stage the code, split it in two. Yeah, and it comments. Yeah, I think it doesn't know what it's talking about. And no, there's something wrong. Yeah, we might need to split the code. Yeah, I'll close this canvas thingy. Currently train 200 lines. This will be like 300. It shouldn't be. While the TensorFlow configuration code is included, it depends on the user confirmation. Ensure that this process works. Okay, let's see. Let's do a training run. See how we go. Yeah, so it's asking us to enter a number of epochs, or we can just hit enter for the default of 15 to be used. Same batch size, default is 32. A learning rate 0.001. That's okay. Proceed with training of 15 epochs, batch size 32, learning rate. Yes. You have to type in yes. And we are training. Yeah, I can't really see the results really well from here, but yeah, I'll just let it train. Okay, it finished at accuracy of 0.7 and area under the curve of 0.8. But the loss is high. Do we want to convert the model to TensorFlow JS? Yes. We get an error. Get an error. Yeah, we have no web model. I think it meant to be stored in the web model folder. We have misclassified images. No, which is weird. Heat maps, no heat maps. Model checkpoints. Okay, we have training plots. training and validation accuracy. Yeah, those are not great, are they? They are not great. So do I upload the image or the actual text results? Oops. If you can comment without any code, that will be greatly appreciated.
These plots show the training and validation accuracy and loss over 15 epochs. The training accuracy steadily improves, but validation accuracy fluctuates significantly, indicating potential overfitting or instability during training. Similarly, the training loss decreases consistently, while validation loss spikes and falls irregularly, suggesting that the model is struggling to generalize to the validation data. To address this, consider 1. Regularization. Increase dropout or add L2 regularization to reduce overfitting. 2. Data augmentation. Expand augmentation techniques to provide more varied data for better generalization. 3. Learning rate adjustment. Reduce the learning rate to stabilize training and validation performance. 4. Class imbalance. Double check if the minority class is adequately balanced with oversampling or augmentation. The training script has run into several issues during execution, which need to be addressed sequentially. 1. Training results. The training process completed with a test accuracy of 76% and a test AUC of 0.81, which is moderate but below the desired performance. The training loss consistently decreased, but the validation metrics, accuracy and loss, fluctuated, indicating potential overfitting or instability in the training process. 2. TensorFlow.js conversion error. The TensorFlow.js model conversion failed due to a duplicate weight name, kernel, in the model, which suggests an issue with the layer naming or saving process. This needs debugging by ensuring all layers have unique names or exporting the model in a consistent format, e.g. .keras format instead of DH5. 3. GradCam error. The GradCam visualization failed because the model has not been explicitly called on any input data before attempting to access its layer's outputs. This can be fixed by running a dummy prediction, model.predict, on a sample input before generating GradCam heat maps. 4. GPU registration errors. Warnings related to GPU libraries, QFT, QDNN, QBLAS, indicate potential conflicts or redundant initializations, but they don't appear to affect the training directly. However, they should be addressed by reviewing your GPU environment setup to avoid unnecessary resource usage. Steps to fix the issues. 1. Model conversion. Remove the deprecated save format argument from model.save calls. Explicitly save the model in .keras format for conversion. Debug the duplicate weight issue by inspecting the layer names and ensuring they are unique. Consider reinitializing the model or using a simpler structure if necessary. GradCam fix. Add a dummy forward pass using model.predict xtest1 or model xtest1 before calling make GradCam heatmap. 3. The code can be split into modules for better organization and flexibility. A data loader module will handle loading, pre-processing, and class balancing. A model definition module will define and compile the CNN and handle saving or converting the model. A train model module will handle training, callbacks, and saving logs or plots. An evaluation module will manage evaluation, confusion matrices, and GradCam visualizations. A front-end utils module will package results for the web front-end and handle TensorFlow.js validation. Finally, a main script will coordinate all modules for end-to-end execution, ensuring modularity and easier debugging.
Yeah, having lunch at the moment, so can you give a general overview of what is it we are trying to do?
You're working on training a machine learning model using the breast-NIST dataset to classify breast lesions as benign or malignant. The goal is to improve the model's performance while keeping it simple and efficient, avoiding unnecessary complexity like ResNet architectures unless needed. The code is being updated to better handle tasks like saving training results, generating GradCam visualizations, and converting the model to a web-friendly format for deployment. You're also transitioning from Flask to a lightweight JavaScript frontend to reduce server load and streamline user experience.
How big is the ResNet model? Currently, what we have, the Keras model that we have at the moment is 134 megabytes. How much bigger a ResNet would be or is?
The size of a ResNet model depends on the specific variant. For example, ResNet 18 has around 11 million parameters. ResNet 50 has about 23 million. And larger versions like ResNet 101 or ResNet 152 have even more. In terms of file size, ResNet 18 typically ranges between 40 to 80 megabytes, while ResNet 50 can go up to 100 megabytes or more. Comparatively, your current model at 134 megabytes seems larger because it might include additional metadata, stored weights, or overhead from saving it in the legacy HDF5 format. A properly optimized ResNet 18 might actually be smaller than your current model, but ResNet 50 or larger would be significantly bigger, likely exceeding 200 megabytes.
So what do we currently have in the model saved that makes it so large? And can you specifically explain, like say ResNet 18, what its exact size is and the model complexity and the reason for it being having that many parameters? Can you explain all that briefly?
Your current model is likely large due to factors like high resolution input images, 224 by 224 with one channel, the saved optimizer state, and additional metadata included in the H5 or Keras format. Saving in these formats captures all weights, model configuration, and sometimes training states, which can inflate the size significantly. Additionally, large dense layers, even in simpler models, contribute a lot to size since each connection requires a weight and a bias. For ResNet 18, the model is relatively lightweight in terms of parameters, approximately 11 million, but its size and storage is influenced by the precision of weights, usually float 32. This typically results in a size of around 40 to 50 megabytes. Its complexity comes from its architecture, which introduces residual blocks to address vanishing gradient issues. These blocks add skip connections, allowing the network to learn more effectively in deeper layers without drastically increasing the number of parameters. Despite this, ResNet 18 is efficient because it uses fewer filters per convolutional layer compared to larger ResNet variants, balancing performance and size.
So do you think it's worth doing a comparison of the current model we have to ResNet 18?
Yes, it's worth comparing your current model to ResNet 18. ResNet 18 is lightweight for a residual network and could offer better performance due to its deeper architecture and residual connections, which are effective for extracting complex features. By comparing, you can evaluate if ResNet 18 achieves higher accuracy or AUC on the BreastMNIST dataset while maintaining reasonable training time and model size. If ResNet 18 performs significantly better without adding excessive overhead, it might justify the switch. However, if your current model is already close in performance, sticking with it could save time and resources. The key would be to experiment and directly compare metrics like training time, validation accuracy, and test performance between the two models.
Can we take the original data file and we would like to generate the instructions for pre-processing, training for the whole pipeline. From scratch. If considering all the elements we discussed in this conversation. Because we're getting a bit stuck up thinking starting from scratch. So back to the original compressed breast M needs 224.npz file.
Starting from the original compressed breastnist.npz file, here's how you can approach building the pipeline from scratch. This considers all elements we've discussed, including preprocessing, training, evaluation, and deployment. 1. Loading and inspecting the dataset. First, load the .npz file to access training, validation, and test splits, train images, train labels, etc. Inspect the dataset to confirm shapes, label distributions, and pixel intensity ranges. This ensures the data is as expected. 2. Pre-processing. Normalize pixel values to the range 0, 1 if not already done. Add a channel dimension to reshape images to 224, 224, 1 for grayscale inputs. Handle class imbalance using techniques like oversampling, undersampling, or synthetic data augmentation for the minority class. Ensure pre-processing steps are consistent across training, validation, and test datasets. 3. Data augmentation. Use an augmentation strategy for training data to improve generalization. Apply transformations such as rotation, zoom, width-height shifts, and horizontal flips. Balance this to avoid overfitting to augmented patterns. 4. Model architecture. Start with a simple CNN, similar to your current model, and refine it if performance is unsatisfactory. Include convolutional layers with increasing filters, max pooling layers, and dense layers with dropout for regularization. Optionally, compare this with ResNet 18 or another lightweight architecture. Save this model in .keras format for compatibility and modern standards. 5. Training configuration. Use a standard loss function like binary cross entropy and metrics such as accuracy and AUC. Include class weighting if there's an imbalance. Use Atom as the optimizer with a starting learning rate of 0.001. Add early stopping and checkpoint saving to avoid overfitting and ensure the best model is saved. 6. Evaluation and metrics. Evaluate on the test set after training. Save metrics like accuracy, AUC, confusion matrix, and misclassified examples. Plot training and validation accuracy loss over epochs to analyze learning progress. Use GradCam to generate interpretability visualizations for correctly classified and misclassified samples. 7. Deployment preparation. Convert the trained model to TensorFlow.js format for deployment on a web interface. Address any issues during the conversion process, such as weight naming conflicts. Test the converted model with sample inputs to validate correctness. 8. Front-end integration. Design a web-based visualization similar to your RhythmScan tool. Include options to upload images and view model predictions. Display results like confusion matrices, performance metrics, and GradCam heat maps. Optimize the interface for usability and ensure smooth client-side interaction. 9. Performance comparison. If needed, train ResNet 18 using the same pipeline and compare its performance with your current CNN. Compare metrics like test accuracy, AUC, training time, and model size to decide if switching is beneficial. 10. Iterate and optimize. Based on initial results, tweak pre-processing, model architecture, or training configurations. Use feedback from evaluations, e.g., misclassified images, to refine the model further. This approach builds the pipeline from scratch while incorporating all discussed enhancements, ensuring a clean slate and a clear progression toward a deployable solution.
Yeah, what expert normally will be reviewing this type of data and making a diagnosis?
Breast MNIST data is typically reviewed by radiologists if it represents imaging like mammograms, focusing on patterns indicating benign or malignant lesions. If the data is histopathological, pathologists examine tissue samples for cell abnormalities. These experts work together, often alongside oncologists, to ensure accurate diagnoses and treatment plans.
Never say never.
AI. If you don't have access to an expert for a second opinion and the cost is a concern, you could consider using an AI-based diagnostic tool as a supplementary option. Tools like those trained on datasets like BreastMNIST can provide insights by classifying images into categories like benign or malignant. However, these tools should never replace professional medical advice. Other options include accessing online platforms where radiologists or pathologists offer affordable reviews, or consulting healthcare programs that provide second opinions at reduced costs. Local teaching hospitals or medical schools might also have initiatives where supervised trainees review cases at a lower expense. AI tools should not replace professional medical advice because they are meant to assist, not act as final decision makers. While AI can provide helpful insights, it may not fully account for the complexities of individual cases, such as patient history, other diagnostic tests, or subtle variations in data that experts recognize. AI systems can also make errors, and a medical diagnosis has significant consequences. That said, AI can still be incredibly valuable as a supplementary tool, especially in regions with limited access to specialists. It can guide users on when to seek professional opinions and support experts by flagging areas of concern. But the ultimate diagnosis and treatment decisions should come from trained medical professionals. You're right. Never say never. AI technology is advancing rapidly, and with proper validation, regulatory approval, and ethical oversight, there might be scenarios in the future where AI plays a more primary diagnostic role, especially in underserved regions or for triaging cases. For now, the best practice is to treat AI as a powerful assistant that enhances rather than replaces human expertise. With continued development, AI might one day bridge gaps where specialists are unavailable. But until then, collaboration with medical professionals remains key. To build the pipeline from scratch, we focus on loading and inspecting the BreastMNIST dataset, pre-processing it with normalization and reshaping, training a simple CNN with augmentation, evaluating metrics like AUC and confusion matrices, and deploying a TensorFlow JS model with an interactive front end. The goal is to create a robust end-to-end process that integrates GradCam visualizations and client-side inference. Do you want to prioritize optimizing the current CNN or directly compare its performance with ResNet 18 during this rebuild? ResNet 18 performs better than your current CNN because of its deeper architecture and residual connections, which help address key challenges in training deep networks. 1. Depth for feature extraction. ResNet 18 has 18 layers, which allow it to extract more complex and hierarchical features compared to your simpler CNN. Deeper networks can capture subtle patterns, like textural differences in medical images, which are crucial for distinguishing between benign and malignant samples. 2. Residual connections prevent degradation. ResNet 18 introduces shortcut connections that skip layers, addressing the vanishing gradient problem common in deeper networks. These connections allow the model to learn residual mappings, the difference between the input and output of a layer, ensuring that deeper layers still contribute meaningfully without degrading performance. Number 3. Wider representational power. With more filters and layers, ResNet 18 can represent more diverse features, which is particularly useful for breast MNIST data if the images have high variability or subtle distinctions. 4. Generalization and pre-training. ResNet 18 is often pre-trained on large datasets like ImageNet, providing a strong starting point for transfer learning. Even if you train from scratch, its architecture is optimized for robustness and generalization. In contrast, your current CNN is simpler, which makes it faster to train, but potentially less capable of capturing the full complexity of the dataset. ResNet 18 strikes a balance. It's deeper and more powerful, but still efficient enough for tasks like breast NIST classification. Your current CNN model is scalable, and it can be made more complex if absolutely necessary. The architecture you're using is a foundational CNN with standard layers, making it relatively straightforward to expand or enhance. Here's why and how it could be scaled. Why the current CNN is scalable. 1. Modularity. Each component, convolutional, pooling, dense layers, can be extended incrementally without redesigning the entire architecture. 2. Efficiency for simple datasets. For datasets like breast MNIST, the current model is sufficient for quick iterations. If performance improves with parameter tuning or better pre-processing, you might not need to switch to a larger model. How it can be made more complex. 1. Increase depth. Add more convolutional layers to extract deeper features. This increases the model's capacity to recognize subtle patterns. 2. Widen layers. Increase the number of filters in each convolutional layer, which allows the model to capture more feature variations. 3. Incorporate residual connections. Borrow concepts from ResNet by adding shortcut connections to help deeper layers contribute effectively without causing degradation. 4. Add specialized layers. Include attention mechanisms, batch normalization, or dropout layers to improve generalization and stability. 5. Switch to transfer learning. Integrate a pre-trained backbone like ResNet 18 or VGG and fine-tune only the classification head. Practical recommendation. For now, keep the model simple and focus on improving training with better pre-processing, balanced datasets, and parameter tuning. If the performance remains suboptimal, After these optimizations, scaling the current architecture is a logical next step before jumping to a heavier model like ResNet 18. This way, you maintain efficiency while exploring complexity only if absolutely necessary. Splitting the training code into modular sections will make it more manageable and allow you to focus on improving each stage independently. Based on what you've outlined and the requirements, the next steps for the development of the training pipeline involve breaking it into these key modules. 1. Data loading. A script dedicated to loading the .npz dataset, extracting the training, validation, and test splits, and verifying the integrity of the data, e.g., checking for missing or corrupted entries. This module can also include reshaping and scaling the images to ensure consistency before further processing. 2. Pre-processing. This includes normalization, resizing, and handling class imbalance. Use augmentations or oversampling to address minority classes. Ensure the outputs are structured and ready for the training stage. Save pre-processed data if needed so it can be reused without repeating this step. 3. Model definition. A standalone module to define the CNN architecture. This keeps the model structure separate and allows for easier experimentation with different architectures or parameter tweaks. You can include functions to load pre-trained weights or create the model from scratch. 4. Training logic. This module handles the training loop, callbacks, e.g., early stopping, checkpoints, and logging of metrics like accuracy and loss. Include visualization generation, such as training curves, confusion matrices, and GradCam heat maps. The training script should call functions from the data loading and pre-processing modules. 5. Evaluation and testing. A separate script to evaluate the trained model on the test dataset, calculate metrics, and save results. This ensures the training and testing processes remain independent. 6. Deployment preparation. A script for exporting the trained model into formats like .keras, .h5, or TensorFlow.js for deployment. Include testing of the exported model to verify consistency between training and deployment environments. 7. Visualization. A dedicated module or function for generating visual outputs, including training validation loss and accuracy plots, GradCam heat maps, and confusion matrices. These can be integrated into the front end for better presentation. Next steps. 1. Split the current monolithic script into these sections, ensuring each module has a clear input-output flow. 2. Start with the data loading and pre-processing modules, as these form the foundation for the entire pipeline. 3. Refactor the training logic to call these modules and ensure modularity. 4. Plan for testing and debugging each module independently before integrating them back into the pipeline. Here's a practical project structure that organizes your training pipeline into clearly defined files and folders. The project structure includes a data folder for raw and pre-processed datasets, a models folder for model definitions and saved models, a training folder for scripts handling data loading, pre-processing training and evaluation, a visualizations folder for accuracy plots, GradCam heat maps, and misclassified images, a results folder for logs and performance metrics, and a front-end folder for web deployment files like index.html, main.js, and style.css. There is also a README MD for project documentation and a requirements text for dependencies.
Just a quick question about the front end folder. If the index.html, should the index.html just be in the main folder so we can actually deploy the whole folder? As is? What do you think?
Yes, placing the index.html in the main folder is a good idea if you plan to deploy the entire folder directly. This simplifies deployment because many web servers and hosting platforms automatically look for index.html in the root directory as the entry point for the application. However, keeping the front-end files in a dedicated front-end folder helps maintain a clean structure, especially in projects with multiple components like data, models, and training scripts. In this case, you can adjust your deployment configuration to point to the frontend/index.html file. The choice depends on your priorities. Simpler deployment. Place index.html in the root directory. Better organization. Keep it in a front-end folder and adjust deployment settings accordingly. Would you like help deciding based on your deployment approach?
Okay, couple more questions. With the models, where do you actually get the ResNet model from? Is it the Python code that we can generate from scratch, or are we downloading the model from somewhere? I actually have a preference to generating everything from scratch if possible. What eventually should be in the web model folder? What type of files? I assume that's the one we deploying using JavaScript onto the front end. Now with the GradCam heat maps, are we just doing it for a single example image, or we can select which image we're doing it for, or are we doing it for all the images if not way too heavy? Do you, by the way, remember how many images are currently in this dataset?
ResNet model origin. You can either 1. Generate it from scratch using Python code. This means defining the ResNet 18 architecture yourself in a Python script using libraries like TensorFlow or PyTorch. This approach aligns with your preference for generating everything from scratch. 2. Download pre-trained weights. Pre-trained ResNet models are often available from TensorFlow or PyTorch model hubs. You can use these as a starting point and fine-tune them on your dataset. If you prefer generating from scratch, you can programmatically define ResNet 18 following the original paper's architecture without relying on downloaded weights. Let me know if you'd like a detailed breakdown of the architecture. Web model folder content. When deploying the model using TensorFlow.js, the web model folder should include the following. 1. Model.json. This file contains the model architecture and metadata in JSON format. 2. Binary weight files. These are .bin files that store the weights and biases of the model, split for efficient loading in the browser. TensorFlow.js creates them during the conversion process. 3. Optional metadata files. If needed, you can include metadata describing the model's training or usage for better integration into the front end. GradCam heatmaps. Single image. The current implementation appears to generate GradCam heatmaps for individual test images, particularly focusing on misclassified ones. This is computationally efficient and useful for debugging. Multiple images. You could allow selecting specific images, e.g. from a drop-down or grid in the front end. This avoids overloading the system while keeping interactivity. All images. Generating heatmaps for all images would indeed be too heavy, especially for a large dataset, and is not practical for deployment. Dataset size. The Breast MNIST dataset has 546 training images, 78 validation images, 156 test images. Each image is 224 by 224 pixels in grayscale, making the dataset manageable for most operations. If heatmaps are needed for all test images, 156, it might be feasible, but for larger subsets like training or validation, it could strain resources. Let me know how you'd like to handle these aspects, and I can help refine the approach. The next steps for code development based on our discussion are: 1. Split the code into modules, data loading and preprocessing. Create a script, dataloader.py, to handle loading the Breast MNIST dataset, normalizing, reshaping, and augmenting the data. Include a class balancing mechanism. Model definition. Move the current CNN model definition to a separate script, basemodel.py. Optionally, define ResNet 18 or other architectures in a similar manner for comparison. Training script. Refine train.py to focus on training and evaluation, pulling preprocessing and model definitions from the above modules. 2. Visualizations and results. Generate and save GradCam heatmaps for misclassified images. Ensure they are limited to manageable subsets, e.g. test misclassified images. Save performance metrics, e.g. accuracy, AUC, confusion matrix, as JSON or text files for front-end integration. Include a utility, visualization.py, to create and save accuracy loss plots and GradCam overlays. 3. Web model conversion. Debug and fix TensorFlow.js conversion issues, e.g. duplicate weight names. Ensure the web model folder, webmodel/, contains the required model.json and .bin files for deployment. 4. Front-end integration. Adjust the index.html to load the TensorFlow.js model from webmodel/. Add interactivity to select an image for GradCam analysis or input new test images. 5. Dataset experimentation. Ensure data augmentation is balanced and not overly repetitive for minority classes. Perform a trial with the current CNN and compare against ResNet 18 to determine performance differences. 6. Error debugging. Address conversion errors, duplicate weight name kernel during TensorFlow.js export. Debug GradCam script to handle layer not called issues by ensuring the layer is properly connected to the model. 7. Documentation and logging. Create a readme.md for developers, documenting the data flow and how to execute each part of the pipeline. Log training configurations and results in a standardized format for reproducibility. Would you like help focusing on a specific module or debugging one of the issues first?
Can you write terminal script for Ubuntu to generate all the files and folders? Keep the files empty for now. Okay, there's a couple of things. So first we said we would not have a front-end model. The index HTML, CSS, and JavaScript can just go into the main folder. Now we don't really need a README. Well, because all the information should be at the bottom of the HTML page eventually. Maybe you can draft the index HTML already. So yeah, we won't have a front end. We update that without, yep. Just have them in the root folder. And we have example for the HTML. And let's check how it looks like. Okay, press the MNIST visualization model performance. Select an image for GradCam visualization. Okay, that looks good, except training metrics. Yeah, we need training metrics for the whole model. I want to update the project structure. Should have updated. Yeah, we have updated project structure. Okay, we have this updated project structure. If you can comment on that briefly, that would be great. Also, can we double check what did we discuss? So will we have an option for the user to upload an image or not? I'm more inclined not to have that option right now, but can you convince me otherwise?
The updated project structure looks clean and streamlined for your needs. The separation of concerns is well organized. 1. Front-end files in root. Having index.html, main.js, and styles.css in the root makes deployment simpler as the folder can be served directly. 2. Data organization. The data folder neatly organizes the raw dataset, exported images, and process training splits, which is crucial for reproducibility. 3. Model files. Keeping base model.py and ResNet88 model.py alongside saved models .h5, .keras, and web model allows for both experimentation and easy web deployment. 4. Results folder. Clear separation of logs, GradCam outputs, misclassified images, and training plots makes it easier to analyze and debug model performance. 5. Scripts folder. Essential scripts for data handling, training, visualization, and conversion to TensorFlow.js are logically grouped, improving maintainability. On image upload. Currently, without user-uploaded image support, the application primarily displays results from predefined datasets. This simplicity reduces server load, ensures consistent performance, and aligns with your current goals of avoiding back-end complexity. However, allowing image uploads could 1. Engage users. Users could test the model with their own data, making the tool more interactive and relevant. 2. Expand use cases. This feature could simulate real-world scenarios, enhancing educational value and potential research applications. 3. Feedback opportunities. User-uploaded images might uncover edge cases or inaccuracies, offering valuable feedback for model refinement. If bandwidth or computation is a concern, you could restrict image size, limit uploads to small image dimensions, and enforce file type constraints. Client-side validation. Perform basic image pre-processing directly in the browser to reduce server load. Would these benefits and mitigations sway your preference toward implementing an upload feature?
Yeah, not sure. Uh, we might leave it open for now. Well, because we still have to train the model. So currently we only have the HTML file contents, which script should we focus on next?
It makes sense to leave the image upload feature open for future consideration, since your primary focus right now is training and improving the model. Given your current progress and the project structure, I recommend focusing next on the train.py script. Why train.py? 1. Core pipeline. It defines the training process, which is the backbone of your project. Refining this script ensures you have a robust model to work with. 2. Result outputs. This script determines how well the model performs and generates outputs like training plots, GradCam visualizations, and logs. 3. Next steps alignment. After training, you can focus on integrating the model into the web interface, index.html and main.js, or exporting it for web deployment, convert to tfjs.py. Once train.py is finalized, validate the training pipeline with the dataset. Dataloader.py may need tweaks if issues arise. Use visualization.py to refine performance outputs like plots or GradCam heat maps. This flow ensures a clear progression toward model deployment while keeping the front-end integration ready for when the model is trained and tested. The provided train.py script is designed to load the breast MNIST dataset, pre-process it, train a simple convolutional neural network, CNN, and save both the results and the model. Here's a summary. 1. Dataset loading and pre-processing. The script loads the dataset from a .npz file, normalizes pixel values to a 0-1 range, and reshapes the data to include a channel dimension. It also handles class imbalance by computing weights for each class. 2. Model definition. A CNN with 3 convolutional layers, max pooling, and dropout is defined. The model is compiled with the Atom optimizer, binary cross-entropy loss, and metrics including accuracy and AUC. 3. Training process. The model is trained for 15 epochs with a batch size of 32, using early stopping and checkpoint callbacks to save the best model. 4. Results visualization. Training and validation accuracy and loss are plotted and saved as PNG files for performance review. 5. Evaluation. The script evaluates the model on a test set, calculating metrics like test accuracy and AUC, and saves these results to a JSON file. 6. Model saving. The trained model is saved in both .keras and .h5 formats for future use. This setup enables a straightforward end-to-end pipeline for training and evaluating a simple CNN on breast MNIST data, with results ready for visualization and deployment. The train.py script in its current state is functional, but requires some adjustments and clarifications to ensure it runs seamlessly and aligns with your goals. Here's a practical assessment. What will work? 1. Data loading and pre-processing. The dataset loading and normalization steps are straightforward and should work if the breast MNIST 224.npz file is properly formatted and available at the specified location. 2. Model definition. The CNN architecture is simple and should compile without issues. It is suitable for initial experimentation. 3. Callbacks. Early stopping and model checkpoint callbacks are well implemented and will help manage training efficiency and save the best model. 4. Visualization. The training and validation accuracy loss plotting is correctly implemented, providing insights into the model's learning process. What needs further modifications? 1. File paths. Ensure all paths, e.g. to the .npz file, output directories, and saved models exist and are accessible. The script assumes a specific directory structure. 2. Hyperparameter adjustments. Default values for epochs, batch size, and learning rate might need tuning for optimal performance. You should also test with a smaller dataset subset to verify functionality before full training. 3. Error handling. Add checks to validate that the dataset is properly loaded and contains expected keys and shapes. This ensures the script doesn't crash if there's an issue with the data. 4. Logging. While some results are saved, additional logging for metrics like confusion matrices or GradCam visualizations could make the training process more informative. 5. TF.js conversion. Ensure the TensorFlow.js converter process works as expected, and address issues like duplicate weight names or version conflicts. Shash optional enhancements. 1. Class imbalance handling. While class weights are computed, you might consider oversampling or data augmentation techniques for the minority class. 2. Scalability. If you plan to add more complex models later, modularize the code to easily plug in other architectures, such as ResNet. 3. Testing. Include a smaller test case to quickly validate the training pipeline without consuming excessive resources. With these adjustments, the train.py script will not only run as intended, but also be more robust and adaptable for future iterations. Let me know if you need to refine specific parts. The updated training script includes several improvements to make it more robust and user-friendly. Firstly, I added error handling to ensure the dataset exists and contains the expected keys before the script runs, preventing crashes due to missing or incorrect data. Secondly, I implemented handling for class imbalance using the compute class sort weight function to dynamically calculate weights for the classes based on the dataset distribution, which improves training fairness for underrepresented classes. The code structure has been modularized by introducing a function to build the model, making the script cleaner and easier to maintain or adapt for different architectures. Training metrics such as accuracy and loss are now plotted and saved as images in a dedicated results folder, allowing for better tracking and analysis of the model's performance over time. Additionally, test performance metrics like accuracy and AUC are saved in a structured JSON file for future reference. The script dynamically creates directories for storing models, plots, and logs, ensuring that output is well organized and does not overwrite existing files. The updated code also logs training progress and outputs useful debugging information at every stage, such as data shapes and class weights, making the training process more transparent. These changes collectively enhance the script's usability, reproducibility, and readiness for deployment.
Okay, so we did another training. Here we get to a pretty high accuracy. So area under the curve of 0.9. Validation loss of 0.6 seems a bit high. Can you explain the output? And if there's any other issues in it, we need to know.
The training output shows significant progress in terms of accuracy and AUC, but there are a few points to address regarding validation loss, model performance, and possible areas for improvement. Summary of results. 1. Training progression. Accuracy increased steadily, reaching a high value of around 92% by the final epoch. The AUC, area under the curve, also improved significantly, indicating better discrimination between the two classes, peaking at top 0.97. 2. Validation metrics. The validation loss improved early on, but plateaued after epoch 10 and even increased slightly towards the end. Final validation accuracy was 87.18% and AUC was 0.92, showing good but not perfect performance. 3. Test set performance. Test accuracy, 83%, and test A.89 are reasonable and suggest the model generalizes fairly well. However, the higher validation loss relative to the training loss, 0.69 validation loss versus 0.36 training loss, may indicate slight overfitting or noise in the validation set. Key observations. 1. Validation loss plateau. The validation loss did not improve beyond epoch 10 and even started increasing slightly. This could indicate overfitting to the training data or a need for further tuning, such as regularization adjustments, increase dropout, or add L2 regularization. Early stopping. Consider halting training earlier to prevent overfitting. 2. Validation accuracy versus loss. The validation accuracy and AUC are quite strong despite the validation loss being higher. This discrepancy suggests that while the model is correctly classifying examples, its confidence in predictions might vary, which is reflected in the higher loss. 3. Test metrics. Test accuracy, 83%, is lower than validation accuracy, which is expected but suggests that the model could still benefit from more generalization techniques, e.g., better data augmentation or additional validation. 4. Training and model saving. The training results were successfully logged and plotted. The model was saved in both H5 and Keras formats. The warning about the HDF5 format being deprecated in TensorFlow 3 is informational and doesn't affect functionality, but suggests switching to the native Keras format in the future. Next steps. 1. Focus on validation loss. Review potential sources of noise in the validation set, or consider adjusting the train val split. Explore additional regularization techniques or hyperparameter tuning to balance training and validation performance. 2. Evaluate GradCam visualizations. Generate GradCam heat maps for test or validation samples to verify that the model is focusing on meaningful regions in the images. 3. Data augmentation. Confirm if further data augmentation might benefit generalization, particularly for minority classes. 4. Hyperparameter tuning. Experiment with learning rates or batch sizes to refine performance further. 5. Compare to baselines. Use a simpler model like ResNet 18 for comparison to understand if the custom model is optimal or if a pre-built architecture performs better on this dataset. By addressing these steps, the model can be further refined for better generalization and reduced validation loss. Let me know how you'd like to proceed. The graphs show how training and validation metrics evolved over 15 epochs. 1. Training versus validation accuracy. Training accuracy steadily increases, peaking near 0.92, showing the model is learning the patterns in the training data. Validation accuracy rises initially, but fluctuates after Epoch 10, suggesting potential overfitting as the model becomes more specialized to the training data. 2. Training versus validation loss. Training loss steadily decreases, indicating the model is minimizing errors on the training set. Validation loss shows a general downward trend, but rises slightly after Epoch 10, reinforcing overfitting concerns or noise in the validation set. The increase in validation loss, while accuracy remains high, suggests that while the model can correctly classify samples, its predictions may lack consistent confidence. To improve generalization, consider tuning regularization parameters, adjusting data augmentation, or implementing cross-validation. This table compares various models and methods on the BREST-MNIST dataset in terms of AUC, area under the curve, and ACC accuracy. 1. ResNet 1828 achieves the highest accuracy, 86.3% among the listed models, with an AUC of 0.901. 2. Google AutoML Vision has the highest AUC, 0.919, but a slightly lower accuracy, 86.1%. 3. ResNet 50 models, while more complex, perform slightly worse than ResNet 18, suggesting diminishing returns with increasing complexity for this dataset. 4. Simpler automated solutions like AutoKeras and AutoSclearn underperform compared to manually tuned ResNet models. If accuracy and AUC improvements are needed, ResNet 1828 or Google AutoML Vision are good references for potential targets. However, consider simplicity and computational efficiency when deciding on the next steps. The model in the train.py script is a simpler convolutional neural network, CNN, compared to ResNet 18 or Google AutoML Vision. Here's a comparison. 1. Architecture complexity. TrainPy model consists of 3 convolutional layers with 32, 64, and 128 filters, each followed by max pooling layers, and 2 dense layers, one with 128 neurons and 1 output layer with sigmoid activation. This makes it a lightweight model with significantly fewer layers and parameters than ResNet 18. ResNet 18 features 18 layers, including residual blocks, designed to overcome vanishing gradients and learn deeper hierarchical features. ResNet 18 has a much larger number of parameters, making it more complex but more capable of capturing intricate patterns. Number 2. Performance. The train.py model achieves a test accuracy of 83% and a test AUC of 0.89 after training. While reasonable, it does not match ResNet 18's AU of 0.901 and accuracy of 86.3%. ResNet 18 generally performs better, as seen in the table, especially for high-dimensional image data like BREST-MNIST. 3. Flexibility and scalability. The train.py model is simpler and faster to train, but may not generalize as well or achieve as high a performance as ResNet 18 due to its limited capacity. ResNet 18 is more scalable and better suited for tasks requiring high accuracy and robustness, but it is computationally more demanding and might not be ideal for quick experimentation or deployment on resource-constrained environments. 4. Model size. The train.py model is lightweight, with smaller file sizes for trained weights, in the range of 134 megabytes. ResNet 18 has a significantly larger size, typically around 44 megabytes for the weights alone, but would increase when fine-tuned for a dataset. Conclusion. The train.py model is a good starting point for simplicity and efficiency. However, if higher performance is critical and computational resources permit, integrating ResNet 18 or a similar architecture could provide better results. That said, the decision to move to ResNet 18 should balance training time, complexity, and performance gains.
I don't know, to me it looks like it's doing quite well as it is. So it is a much simpler, so 3 convolutional layers instead of 18 in ResNet 15. So interestingly enough, like adding more layers doesn't improve performance. So ResNet 50 actually had the slightly increased performance. Yeah, so our performance at the moment is actually fairly close to ResNet 50. Interestingly, the number of pixels doesn't make a difference. I mean, surely you have more resolution in the image, you should get better performance. So my hypothesis will be that with 224 by 224 pixels, you can achieve even higher performance, going to 0.99 and so on and so forth. But the current results didn't show that. Does it happen for all datasets as well? Yes, some of them are a bit oversaturated as they are. Yeah, maybe you can explain in relation to the other datasets, a training on the other datasets as well in the table provided. We eventually need to actually explain all these as text at the bottom of the front page, at the bottom of the HTML. Just something to keep in mind. But yeah, to me, yeah, please convince me otherwise, but it seems like our performance is actually better than, considering how much simpler the model is, so relatively the performance is better. So essentially there is, can you talk about the bottleneck, the threshold of the number of layers? So obviously it seems like more layers doesn't mean better results. What do you think? Can you do continuous code? I'm using text to speech. Can you actually store this in your memory? I'm most of the time using text to speech, so if you can optimize your responses to that, that will be great.
Your observations are quite accurate. The number of layers alone doesn't guarantee better performance, as shown by the comparison of your simpler CNN with ResNet 18 and ResNet 50. While ResNet 18 and ResNet 50 have deeper architectures and are better at capturing complex patterns in larger datasets or more diverse features, your three-layer model performs impressively on BreastMNIST, given its simplicity. The diminishing returns on performance with increased resolution and complexity might indicate that the dataset is already well represented at 224 by 224 pixels, and the model's capacity is sufficient to capture the necessary features. In datasets like BloodMNIST or PathMNIST, this might be different, as they seem to saturate at higher resolutions with more complex models. It could be beneficial to train your current model or ResNet 18 on other datasets from the table to see if similar trends persist. This insight can be a great addition to your HTML documentation, as it would contextualize your model's effectiveness relative to complexity and dataset characteristics. Would you like to focus on training other datasets next, or refine the explanation for the current model's simplicity and its relative performance?
There is always the main question is, do we deploy now or later? So there's a couple of things in training. During training, what are we saving? In terms of results, I have empty folders, and also except the HTML that we have a template for. Okay, can we update the HTML to show something more meaningful? Also, can you comment on if we should have a browser for the images on the front page or not? What do you reckon? But yeah, we would like to display the current accuracy loss PNG that we have saved. And the logs, we have a metrics JSON file in the logs as well. So we, yeah, we need to update the HTML because currently it's not displaying anything. Or what else? We have some of the other files missing, files and folders. I'll share the structure of the project again, an updated structure of the project, files and folders. Actually, can you specify, can you tell me how to generate using a tree command on Ubuntu in the terminal, how to generate an updated project structure that will actually also have the size of each file? Can we do that somehow? Yeah, we have to do that in. Yeah, we currently have a project structure. Yeah, we'll go into that folder in integrated terminal, a tree project structure with sizes. Okay, now we have it. Okay, the models are empty. Okay, why the models are empty? Oh, we have something in the misclassified images, do we? Misclassified images. In results. Okay, this structure is a bit convoluted. I can't find anything. Don't get it. I can't find the... So we have a web model as well. It looks pretty empty to me. No, that's just the folder. Yeah, that's the that's the size of an empty folder. It's like, okay. And we have 256. Yeah, we have a model. Was that model actually updated? And why is it in scripts? Why is it not in the models folder? It's a bit unusual. Yeah, so currently the model is 128 megabytes. Yeah, also not sure why it's so large. Anyhow, what do we do next? Yeah, we could update the index HTML to display plots and metrics dynamically. That sounds like a solid plan. It's currently 121 lines of code, and now it's 56. What? And it's not actually displaying anything. Well, because we need JavaScript. Yeah, I seem to have too many files. Yeah, I got it all messed up. We got it all messed up. Well, right, the index.html is shorter because it now has a JavaScript. Hey, can you comment on what's going on? Should we just go ahead and generate? We currently don't have anything in the main.js. Is the HTML linking to it at all? Yes, it does. Yeah, so we need the script for main.js. Yeah, but if you can comment on everything else that is going on that very quickly, that would be good as well. Yeah, we did quite a bit of progress today.
Here's a breakdown of what's going on and suggestions for next steps. Current status. 1. Model location. Your models directory contains placeholders, base model.py, resnet18 model.py, etc. But the actual trained models, best model.keras, breast-mnist model.h5, are in the scripts models subdirectory, which is unusual. The trained models should ideally reside in the top-level models directory for consistency and clarity. 2. File sizes. The best model.keras file is 128 megabytes, which is expected for a model with multiple convolutional layers and dense connections. However, the size might seem large because it includes both architecture and trained weights. Empty folders like web model and placeholders in misclassified images should be populated or removed if unused. 3. HTML and JavaScript linkage. The index.html file is correctly linking to main.js for dynamic updates, but main.js is currently empty. This explains why the page doesn't display any dynamic content or plots yet. 4. Metrics and plots. The training results, such as metrics, from metrics.json and plots, e.g. accuracyloss.png, are generated, but the HTML page doesn't yet fetch or display them. GradCam-related folders, GradCam heat maps, misclassified images, are either empty or unlinked in the front end, leading to gaps in functionality. Suggestions for next steps. 1. Organize the model files. Move the trained models, bestmodel.keras, breastmnist model.h5, from script/models to the top-level models directory. Update any scripts that reference these paths. 2. Populate main.js. Implement JavaScript to dynamically fetch and display metrics, plots, and GradCam heat maps, as outlined in the earlier response. This will bring your index.html to life. 3. Remove or populate placeholders. Remove empty folders or populate them with actual content. For example, web model. If this is for TensorFlow.js deployment, ensure it contains the converted model files, model.json and binary shards. Misclassified images. Add images or remove the folder if this feature is unused. 4. Ensure JavaScript integration. Verify that main.js is correctly linked in index.html. Script circles main.js script. You can test this by adding a simple console.log JS linked in main.js and checking your browser's developer console. 5. Test dynamic functionality. After implementing main.js, ensure the page dynamically displays training metrics from metrics.json, accuracy loss plots from results training plots accuracyloss.png, GradCam heat maps based on selected images. 6. Debugging workflow. Clean up misplaced files and unused folders to avoid confusion in navigation. Update your project structure documentation, projectstructure.txt, after reorganization. Immediate action plan. 1. Move trained models to models. 2. Add dynamic JavaScript to main.js to fetch and display metrics from metrics.json, accuracy loss plots, GradCam heat maps. 3. Verify index.html functionality. Here's an outline of what the main.js file should do to bring your index.html to life. Objectives for main.js. 1. Dynamically fetch and display metrics, metrics.json. 2. Display training plots, accuracy loss.png. 3. Allow the user to select images for GradCam visualization. 4. Display GradCam heat maps and the selected image. Script functionality. 1. Fetch and display metrics. Read the metrics.json file from results/logs. Parse and display key metrics like test accuracy and AUC in the training metrics section. 2. Display accuracy loss plot. Use the EMG tag in the accuracy plot section to load accuracy loss.png dynamically. 3. GradCam dropdown. Populate the dropdown with available image file.
Okay, first of all, we're getting a few errors. But also, I would like to simplify the file and folder structure. It's very convoluted at the moment. And there is, for example, the models. Why there are two models folders, subfolders. I don't think we need that, do we? Do we need two models folders or not? Do I have to manually? Do we need to change the folders and files manually, or can we generate the script for the terminal? I am currently in the correct in the project folder. Okay. Yeah, we're just running it from the terminal, so so this is the current groups. Yeah, we're doing all that. And we can verify the structure. Okay, is this the correct structure for the project? Well, we do intend to use the models, but yeah, the fact that they are empty at the moment. What I currently have, can you write the terminal script that I can run directly in the terminal, not in a separate file, not an executable file that I can just run in the terminal to update and finalize the file and folder structure. Yes, is this correct? Is this the correct file and folder structure? Okay, so what do we need to fix in the current version of the index HTML and the main JavaScript for them to work with the current file and folder structure, with the new file and folder structure. I might finish this next time. We're having quite a few issues at the moment. We might start from scratch. As in, no, not from scratch, but you know what I mean. And yeah, we can get the robot to sign us out. So can you sign us out? And give a summary of what we did today and a general overview. And invite the viewers to check out the website.
Today, we focused on refining the BreastMNIST visualization project, addressing folder structure issues, updating the index.html file, and ensuring alignment with the newly structured files and folders. We also reviewed the integration of metrics, plots, and GradCam visualizations dynamically in the front end while troubleshooting JavaScript and HTML functionality. Key progress included simplifying the project layout, ensuring consistency in file paths, and discussing strategies to improve usability. We tackled challenges like debugging incorrect paths, clarifying how to serve misclassified images, and reorganizing files to streamline future development. Next steps will include finalizing the front-end functionality, testing thoroughly, and ensuring smooth deployment. Don't forget to explore Bionic Chaos at bionicchaos.com for more open-source biomedical tools. Feedback is always welcome, and we're excited to share these tools with the community. See you next time.
Bye.